afternoon. Welcome to the online engineering and science tutors. Welcome to yet another video on phase diagram of different solubility. We have complete solid solubility, we have limited solid solubility, we have complete solid insolubility. So we are going to see an example on how to construct this diagram and different elements or alloys that exhibit these different types of solubility curve. The first one we'll be looking here is complete solid solubility. This is a typical example of complete solid solubility curve. Okay, now let's say this is y-axis, which represents the temperature axis, and the x-axis, which represents the composition axis. Now we know from literature that copper is having a melting temperature of 1085 degrees Celsius, and we know nickel is having a melting temperature of 1455 degrees Celsius. Now, if you pick copper and plot it on the x-axis, taking this temperature range, we are going to be seeing that this is 1000, and copper, which melt at 1085 degrees, will have its melting temperature here, right? And then nickel, on the other hand, will have its melting temperature on this axis, because the melting temperature of nickel is far greater than that of copper. So you can see this is 0% nickel and this is 100% copper. Exactly, it is so because at this junction, this axis is representing copper axis, while this axis is representing nickel axis. So when you have 100% nickel, you are not expected to have anything like copper, okay? Because this is 100% nickel, copper should be 0%. Copper should be 0%. When you are going backward, you are reducing copper, so you are reducing nickel by 20%, thereby increasing copper by 20%. If you move further backward, you are reducing nickel by 40%, thereby increasing copper by 40%. The same thing applies here. You are having 100% of copper here, nickel should be 0% here. So that is what it means. So now if you plot this graph, and this curve is gotten from cooling curve. It's gotten from cooling curve, whereby each point is located. This is where your transformation starts, and this is where your transformation stops. Same thing. And then when you complete this point, then you can just draw this curve, and then you have the complete solid solubility. Above this region, we are going to have the liquid region. Okay, where you are heating, and then you pass this melting point, anything that falls above this line, you call it liquid region. Below this line, you are going to have solid solution. And this solid solution can be represented with capital letter S. Okay, then between this liquid region and solid region, you are going to have a two-phase region, which is liquid plus solid region. Now, this line, for identification purpose, we call it the liquidus line. And this line is called the solidus line. So, an example of alloy that exhibits complete solid solubility is copper and nickel. We should know that copper melts at 1085 degrees Celsius and nickel melts at 45 degrees Celsius. That is the melting temperature. And then when you have that, you identify the melting temperature of the first element on the axis, and then the second element still on the y-axis, because the y-axis represents the temperature axis. After that, you will now use your cooling curve to get the point of this curve, after which you are going to join this point together and get this curve. So this is a curve of complete solid solubility. So the next curve we'll be looking at is the limited solid solubility. Just the word limited solid solubility. That is, there is solubility, but the solubility is limited. So for us to draw this kind of curve, as usual, we draw this. Here we are going to have the temperature, and then here we are going to have the composition axis. Composition or weight percent. limited solid solubility. An example of element that exhibit limited solid solubility is lead and tin. You can have Pb for lead, and then you can have tin as well. These are the two elements, or these are alloys that exhibit limited solid solubility. I will know that the melting temperature of lead is 327 degrees Celsius, while the melting temperature of tin is 232 degrees Celsius. As usual, this is going to be our tin axis, and this is going to be our lead axis. So here will be 100% lead, and here will be 100% of tin. So taking the temperature, because the temperature is low here, we can have 100, we can have 200, 300, 400, 500 continuously. Then the melting temperature of tin is 232, so we can have 232 somewhere around here, 232. So I should have 232 around here. Then the melting temperature of lead is 327. We can have 327 somewhere around here. So I'll have the melting temperature of lead, which is 327 degrees Celsius. So how do we do this now? We will now find what we call eutectic temperature. Eutectic what? Temperature. And that eutectic temperature could be on 190 something or 195. So I can draw this line, this straight line. Now this full straight line is going to give me what we call eutectic line. It is this eutectic line that transformation occurs through eutectic point. Now I can keep the center line anywhere. Then you know that there is transformation that occurs there. So this line, I use this eutectic point through the melting point of tin, and then the other line will meet this through the melting point of tin, of lead. Since we said there is solubility, that means there will be solubility here, and the solubility is limited. Therefore, I can have a solubility here, so I'll extend this curve downward. Same thing applies here, I'll extend this curve downward, such that there is solubility. So, it's solubility, and this is solubility. So to measure this, to label this diagram now, above this temperature or above this line, we have the liquidous line. Then here, since there is transformation, we use alpha to represent the transformation. Here we use beta to represent the transformation. Within this region, we have the two-phase solid region, which is alpha plus beta. This region, this alpha is sharing boundary with liquid, so we have this alpha plus liquid, and then the transformation to the liquid plus beta. Now you will notice that here I wrote alpha plus liquid, and the other one I'm writing liquid plus beta. It is still the same thing. Why? If I say 1 plus 2, this is definitely the same thing as 2 plus 1. Okay, so that is why you can write alpha plus liquid the same thing as liquid plus beta. So this is how to construct, or this is the curve for limited solid solubility. So the eutectic temperature of this diagram, which is limited solid solubility, is below 200 degrees Celsius. The eutectic temperature of this phase diagram, which is limited solid solubility, is below 200 and having a tin composition of 70%. So if the composition of tin is 70%, therefore the composition of lead will be 30%. So this is just the phase diagram and how to construct the phase diagram of limited solid solubility. Now, if there is need for you to label or identify the different regions or zones or lines on the phase diagram, it's very simple. We know that this line is the liquidous line, and we know that this line is the solidus line. Then this region is solubility region. Then this other line, this line is liquidous line, this one is solidus line. Why this region is solubility region? Why this line is the solubus line? This is the liquidus line, solidus line, solubility region, and the solubus line. And this is our eutectic line. This is the eutectic line, which is below 200 degrees Celsius at a thin percentage of 70%. Okay, thin is 70%, while lead is 30%. And this point is the eutectic point. When you take your transformation and follow this point, you are going to have a transformation of this form, liquid, transforming into alpha plus beta, a two-phase solid region transformation. And this type of transformation is called an eutectic transformation. Any transformation that involves liquid being transformed into two solid phase, we call it eutectic transformation. But if it is a solid phase transforming into a two solid phase, that is, we have the solid 1 transforming into another solid 2 and the other one, last one, which is solid 3, we call this transformation eutectic transformation. This transformation is called eutectic transformation. But whenever liquid is involved, we call that transformation eutectic transformation. Now the next one, or the last one I want to see for this presentation is the complete solid insolubility. That is, you have a curve that is having insolubility. That is the two elements involved, or the alloy, you cannot call it alloy, the two solid phase, the two solid elements involved are not soluble in each other at all composition. As usual, we draw our curve. This curve is our temperature axis, and as well this one is also our temperature axis. Then this is our percentage composition axis. And then an example of such is cadmium and bismuth. This is cadmium and bismuth. Example of elements that exhibit this kind of curve is cadmium and bismuth. Right? Cadmium. So let's write it here. C D is cadmium. Also, you are going to use this place. CD is cadmium, and then Bi is bismuth. So what is the melting temperature of cadmium? The melting temperature of cadmium is 321, and the melting temperature of bismuth is 271 in degrees Celsius. The melting temperature of cadmium is 321, while the melting temperature of bismuth is 271. Now, the eutectic temperature of these two alloys occurs at a temperature of about 140 degrees Celsius. That is where the eutectic temperature of this element occur at about 140 degrees Celsius. So since we have this range of temperature, which is somewhat similar to the curve of limited solid solubility, so here can be 100, 200, 300, 400, and then 500. So we locate the melting point of bismuth, which is 271. So 271 should be here, and then the melting point of cadmium, 321. So 321 should be somewhere around here. Okay, so we just place it down here so that we can locate the melting point of bismuth, which is what, 321 degrees Celsius. And then remember, I said the eutectic point or the eutectic line occurs for this type of phase diagram, which is complete solid insolubility at 140 degrees Celsius. So this should be somewhere 140 degrees Celsius. And at a composition of, let me say, 67% of cadmium. So this is bismuth, and this is cadmium. As usual, this is 100% bismuth, 0% cadmium, and this is 100% cadmium and 0% bismuth. So if that's the case, the melting point of cadmium will come down to this, protective point, and as well the melting point of bismuth will come down to this protective point. Now the curve is complete solid insolubility. There will be no solubility between cadmium and bismuth. That is to say, cadmium will not be able to pass this region, no solubility. Bismuth as well will not be able to pass this region. That is why this line is extended up to this axis. Likewise, the line of solubility is extended up to the axis to show there will be no solubility between bismuth and cadmium at all composition. If that is the case, this region above this liquidous line, we are going to have liquid region. Okay, and then this region is going to be what region? Can we try? Okay, this region is going to be liquid plus A, because this region is A plus B. That is, we are going to have combination of bismuth and cadmium at this region. So let's use A to represent bismuth and B to represent cadmium. So the combination will now be what? Liquid plus A plus B, that is bismuth plus cadmium. This region again will now be B plus liquid. As well, if you are labeling, this will be your liquidous line, this will be your solidus line, and this point will be our protective point. And as well our solidus line. This is our authentic line, and this is our solidus line, this is our liquidus line. This is the melting temperature of bismuth, which is what? 271. Melting temperature of cadmium, which is 321 degrees Celsius. So this is all we need to know in this type of phase diagram, that is the complete solid solubility curve, the limited solid solubility curve, the complete solid insolubility curve, which are all obtained from cooling curve. In our next presentation, we will see how to determine phase fraction using the lever rule. Thank you for watching. Please, if you are a new viewer, subscribe and comment. And if you are an existing viewer, please like and share the video. Thank you. See you in our next video.